We are now talking about the 𝗖𝗄𝗃 design tool. The very first stage of the 𝗖𝗄𝗃 application design workflow consists in the application development, during which, following the predefined 𝗖𝗄𝗃 template, the application developer and the application architect provide the needed configuration files and implementation of the application components to prepare the application for the subsequent execution of the 𝗖𝗄𝗃 design tool. The 𝗖𝗄𝗃 design tool provides a set of important functionalities for the automatic generation of configuration files for both the 𝗖𝗄𝗃 design and runtime tools, and for the automatic design of application components. It consists of high-level abstractions to provide quality-of-service constraints to drive the application deployment, and furthermore, it provides advanced functionalities to configure monitoring files to be used by the 𝗖𝗄𝗃 monitoring subsystem, to provide automatic partitioning of neural networks-based models, and to provide the automatic generation of alternative deployments with degraded performance. Finally, it generates the 𝗖𝗄𝗃 drift detector component at design time to detect data drift at runtime. The 𝗖𝗄𝗃 design tool has been developed to standardize the structures of the application and to provide a simple interface between the user and the 𝗖𝗄𝗃 framework, to set a standard for the organization of files in order to improve the synergy among the 𝗖𝗄𝗃 tools, and furthermore, for the need of advanced functionalities driven by the AI requirements. The design of an AI-based application to be deployed in the computing continuum is not an easy task without 𝗖𝗄𝗃. The developer of the AI application must provide the implementation of the components as well as the configuration files in a non-standard and non-portable structure. Each possible deployment must be explicitly defined in the case of alternative implementation of the components with degraded accuracies and multiple candidate resources. There are no easy ways to define quality-of-service constraints to drive the deployment, and the user must involve AI experts to provide partitioned models. Finally, there are no automatic ways to design detection algorithms for detecting data drift at runtime. With 𝗖𝗄𝗃, the design of the AI-based application becomes much easier. Indeed, both the application developer and the application architect are able to provide the implementation of the components as well as the configuration files and the description of the available resources and candidate assignments in a very easy way by using a well-defined application template. Alternative deployments are automatically generated in the case of components with degraded accuracies, and high-level abstractions are available to define quality-of-service constraints to drive the application deployment. The SPACE4AI-D partitioner tool allows the automatic partitioning of neural networks-based components, and finally, the automatic design of runtime drift detection algorithms can be enabled to detect data drift at runtime. Now, we are going to show the demo in which we demonstrate how to use the 𝗖𝗄𝗃 design tool. In particular, in the demo, we are going to generate a new 𝗖𝗄𝗃 application by using the 𝗖𝗄𝗃 Studio through the available Docker image and the application template. Then we provide an example application, that is the mask detection application, in order to showcase how to prepare the files for the 𝗖𝗄𝗃 design. In particular, we show the component implementation, the application workflow, and the list of configuration files, among which the candidate resource files and the candidate deployments files to drive the application deployment. Then we run the 𝗖𝗄𝗃 design tool, and finally we inspect the generated files. The considered application is composed by two components, the blurry faces and the mask detector. The application takes an image as input, it anonymizes the faces in the image, and finally detects if each person is wearing a mask by classifying the detected faces. The candidate computational layer for the two components belong to the same network domain. Each computational layer has two candidate resources, which are two alternative AWS instances, the M4 large and the X large. Before using the 𝗖𝗄𝗃 design tool, let's see how we can create an 𝗖𝗄𝗃 application and how to prepare it for the design stage. In order to create a new 𝗖𝗄𝗃 application, we can use the 𝗖𝗄𝗃 Studio, whose Docker image is available from the AI Sprint public registry. By using the AI Sprint help, we can inspect the available functions. Among them, we find the design, which executes the AI Sprint design tool, and the new application one, which allows to create a new AI Sprint application by exploiting a predefined template included in the AI Sprint Studio. Let's consider the last one. In order to create the application in the current folder and with the right permissions, we must define some additional Docker arguments. The first one is needed to mount the current directory in the container. The second argument allows to set the mounted directory as the working directory. And finally, the last one defines the user executing the container. The only parameter of the new application function is the name of the new application. In this case, we use mass detection up. Once completed, we can find the new application in the current folder. Let's inspect its content. As we can observe, a set of folders is created. The common config contains several configuration files. The most important for the demo is the application DAG, defining the application workflow, and the candidate resources and deployments. The implementation of the components must be provided in the SRC folder. The iSprint folder will contain the output of the design stage, including the alternative components, designs, and application deployments. Starting from the new empty application, we must prepare the files for the considered mass detection application. In particular, we must provide the implementation of the two components, the application workflow, and the description of the available resources, as well as the candidate deployments. Let's inspect again the application folder after the completion of the files. In the application DAG, we define the name of the available components and the workflow, by defining that the output of the first component will be the input of the second one with probability equal to 1. Then, in the candidate resources file, the application architect defines the available resources, which consist of a single network domain with two computational layers, each one composed by two resources, an M4X large AWS flavor and M4 large AWS flavor. Then, in the candidate deployments file, the list of components is provided, by defining for each one the list of candidate execution layers and resources. For instance, the mass detector component can be deployed on the second computational layer and on both the available AWS flavors. In the SRC folder, the application developer adds one folder for each component containing the requirements files used by the TOSCARIZER to build the Docker image and the main Python script required to execute the component. We can observe how the blurry faces component has several arguments, among which the references to input and output files. The input video is processed by the FFmpeg library to extract the frames analyzed in sequence. Each frame is first read as a RGB image, and after a preprocessing stage, the neural network is loaded and inference is computed by giving the frame as input. The output is the list of detected faces in the image. A blurring filter is applied to each detection to anonymize the faces. Then, the blurred image is finally stored to the output min.io bucket to trigger the execution of the next component. The main Python script of the mass detector has a similar structure. It takes as input the image produced by the blurry faces component, which is first read again as an RGB image, and then fed to the neural network to perform the detection and classification. The detected bounding boxes are then filtered by selecting the ones with a high confidence score. Then, the total number of people wearing a mask is computed, as well as the total number of people not wearing a mask. Finally, the output image, including detections and counts, is stored in the output bucket. In the considered demo, the user defines two constraints by requiring the first component to be executed in at most 15 seconds and the total application to be executed in no more than 20 seconds. At runtime, the execution times will be stored in InfluxDB and monitored, as well as the number of detected masks. The constraints are defined by the user by making use of the AI Sprint annotations. Here, three annotations are used to define the name of the component, the desired local execution time of 50 seconds, and the expected throughput of the whole application, which is 1 image per second. For the mass detector, the component name and exact time annotation are used by defining a global time threshold of 20 seconds and by indicating the blurry faces component as the previous component involved in the constraint. Then, the report metric function from the AI Sprint monitoring tool is used to store the mask count in InfluxDB at runtime. To this end, the mass count, the no-mass count, and the error ratio are stored into a metric field dictionary, which is given as argument to the report metric together with a metric name. At this stage, the preparation of the 𝗖𝗄𝗃 application is completed, and we are ready to execute the 𝗖𝗄𝗃 design by using again the 𝗖𝗄𝗃 Studio through Docker. In this case, we are using the 𝗖𝗄𝗃 design function, which requires the directory of the application as argument, which in this case is again the mass detection hub. During the execution, the 𝗖𝗄𝗃 Studio is logging some information about the automatically parsed DAG, indicating that 2 consecutive components have been found. The 𝗖𝗄𝗃 annotations parser is executed by producing the annotations YAML file as output. Let's inspect its content. It contains a summary of the found annotations for each component, together with the corresponding parameters. So we have the execution time, expected throughput, and component name for the first component, and the component name and execution time for the second one. Finally, the annotation arguments are automatically validated to check for errors and inconsistencies. In the next step, the 𝗖𝗄𝗃 design tool runs the SPACE4AI-D partitioner tool. First, the base components designs are generated. By looking to the 𝗖𝗄𝗃 design folder, we find a base folder for each component, containing the original implementation of the components. Then, in the case of partitionable or early exit models, defined through specific annotations, the partitions are automatically generated. No partitions are generated in this demo. This is summarized by the automatically generated component partitions YAML file, where only the base designs are available for the 2 components. The next stage involves the generation of the base deployment, which can be found in the 𝗖𝗄𝗃 deployments folder. The base deployment uses the base components designs, pointed through the use of symbolic links in the ASRC folder. Also, the application workflow is the original one, as can be noticed in the DAG file. The optimal deployment folder contains an automatically generated production deployment YAML file containing the assignments of the resources. For the base deployment, each component is automatically assigned to its first candidate resource, which is the VM1 for the first component and the VM3 for the second one. Finally, the name of the current optimal deployment is reported, which, at this stage, is the base one. The final stage of the 𝗖𝗄𝗃 design tool is the automatic parsing of the execution time constraints to generate the configuration files needed by the other tools, including the 𝗖𝗄𝗃 monitoring subsystem. The first generated file is the multi-cluster quality of service constraints file, which shows the local and global constraints for each possible deployment and for each execution layer. In the AMS folder, we found the same information, but splitted into separate files, one for each computational layer. After the generation of the quality of service constraints, the 𝗖𝗄𝗃 design tool terminates and the application is ready for the next stages.